this chapter is pretty short. Oh, if you haven't put your Penn email into the chat box, if you can go ahead and do that, that would be awesome. So yeah, basically we're talking about ANOVA. No, I'm not in DC anymore. Actually, yeah, I got back. When did I get back? Saturday. Yeah, I came back Saturday. So here I am. I loved Gallaudet. It was amazing. So I was like, if I don't get in there, I'm gonna cry. So so yeah, it was definitely fun. So but yeah, I hope to go back soon. I'll be down. I have to go back to Virginia tomorrow, I think. I don't know. My schedule's always something. So yeah, I have to drop off the boy, so I gotta drive back down there. So but yeah, so yeah, I'm always traveling and doing something. So but yeah, 4-hour drive, yay. Yeah, in Manassas. But yeah, oops, sorry, I had some soup earlier. But yeah, short chapter this week. This should not take too long. At least it didn't on Thursday. So you guys will be out of here pretty fast. But yeah, so let's talk about ANOVA. So often a question, well, first of all, like ANOVA in general is comparing the means of 3 or more independent groups. So it's one of those things that we kind of use when we have, you know, a lot of independent groups and we want to compare them, and we can't really do that with all the tests that we've practiced so far. So in that case, we want to make sure that we are doing all, you know, all the t-tests. I mean, we're doing the ANOVA test in order to compare these. So so yeah, so basically the first question, you know, is just like, why wouldn't we do a bunch of t-tests? That's often a question because remember, t-tests are the ones that we do use for means. But the main point is here that we would need a lot of tests because, you know, we have so many independent groups, so we'd have to do t-tests for all of those groups and a bunch of them to randomize them, make sure we have large enough sample sizes. And then remember, you know, the more that we do, we are going to increase that chance of having a type 1 error. And remember, type 1 is the incorrect rejection of a true null hypothesis. So reject the null when it was actually true. Say that there's a change when actually there's no change. So that's the main idea there. And we are going to basically need to, like, since if we would increase that, it's also going to inflate alpha. Remember, alpha represents our probability of a type 1 error. And then the one idea here is that we wouldn't have information about the independent variable overall. We would just kind of have information about each one specifically. So that's the main idea there, why we wouldn't use a bunch of t-tests. So yeah, so just to review again, so ANOVA is the same idea that we do a bunch of, you know, we have the same 5-step hypothesis testing procedure that we've been using for all of these. So we have 1 through 5. So first you want to check any necessary assumptions, write that null and alternative hypothesis. Then calculate your test statistic, determine the p-value associated with whatever test statistic you had. And then our last 2 steps are always the same. We're going to decide between our null and alternative hypothesis and then make a real-world conclusion based upon that. So just a review of that. So now we're going to talk about the specific steps that you do take to get this, to actually do it for ANOVA. So our first step, we want to check those assumptions and then write our null and alternative hypotheses. So basically here we're going to compare the however many independent groups we have. You know, it can, as long, you know, basically it's usually, you know, 3 or more. So we're comparing as many independent groups that we have. And then keep in mind that the null hypothesis is that all the group's population means are equal. So that's going to be this one here. And then the alternative is that not all of them are equal. So that's saying that there's some sort of change between them. There is some sort of difference. And then our assumptions, if we go back to the top, you have to make sure that these 3 assumptions are correct. So we have our, the first one is that each sample is an independent random sample. And then our second is that the distribution of the response variable does have to follow a normal distribution. Third, and then the third one, basically, that's saying the variances are equal across the responses. Basically the spread has to be equal across those group levels. And the way that we can check that, if we don't, have the variances already, you can use this rule. So if the largest sample standard deviation out of all your groups divided by the smallest out of all the groups is not greater than 2, then you can assume that the population variances are equal. So if you're not given the variances specifically to see if they're equal, for all of them, then you can just use that rule of thumb, and that'll tell you if this assumption is met here. And then for our second step, remember we have to find that test statistic, and this comes from our mini tab. When we have a mini tab output, it's going to be an F test statistic, a little bit different from what we've been using for means and proportions. Proportions, we use Z, means we use T. And then here we are talking about, it's just talking about, so remember we always have a right tail probability for ANOVA tests, so the test statistic will always be the beginning of our, the beginning of the area that we find the p-value of, so it's going to be the beginning and then everything to the right of it. And then the F test statistic, basically, if we were to define it, it's just our variation between the groups divided by our variation within the groups. So we're trying to decide, because the whole idea is to see what the difference is between them, if there is a difference in general. So that's what we would find there with the F test statistic. Oh, baby. Excuse me. Okay. And then our p-value is also shown here in a mini tab output based upon our F value. So if we were to visualize this, just to remember, we're going to have, oops, go back. Hold on. Draw. Okay, so if we have a normal curve here, because remember it does have to be normal, that's one of the assumptions that has to be met. We're going to have our F value here, and then this is going to be our p-value, this shaded area. So that's based upon our F value and it being a right tail probability. All right, and then, oh, I just saved this screen apparently. Didn't mean to do that. Okay, so our fourth step, you want to decide between their null and alternative hypotheses. So remember, a p-value less than alpha, reject that null hypothesis, and then if it is greater than alpha, we fail to reject. And then, we have this answer, but we want to make sure that we kind of make it applicable to real life. So then you're going to take whatever you found in step 4, then, oh my God, excuse me, and then you're going to make a conclusion based upon the terms of the real world, or in terms of your original research question and the actual variables that you're talking about there. Okay, and then, I know, I know, no, it's okay. I don't even know why I'm so tired. I was writing personal statements all day, maybe that's why, but it's okay. So, and then something else that relates to ANOVA is a post-hoc test, and we often talk about Tukey's. Basically, this is conducted after you do your ANOVA, because your ANOVA kind of tells you, is there a difference between the means or is there not? And then the post-hoc test is basically trying to tell you what specifically is which groups are different from one another. So if you find that they're different, it's going to tell you which ones specifically are different from one another. So you could just do this on Minitab. You can look at the online review notes, that goes step by step through it and everything. But so yeah, you conduct this after ANOVA just to find specifically which groups are different from one another if you found that they are different in general. Okay, wow. Okay, let's do some review questions. So our first review, so we have 2 sets of sample data, A and B, and they're given without doing any calculations, just visualizing these graphs here. Indicate which set of sample data, A or B, there is likely to be stronger evidence of a difference between the 2 population means. So try to answer this one, and then we will go over it together. Okay, yay, good job. So data set A is going to be our answer here, because the question is asking where do we have stronger evidence of there being a difference. So we don't have any overlap between the two different sets here in data set A, while we do have overlap for like this part of for data set B between the two groups. So that means that, we do have a chance of there being no difference, that they are the same here. And we really don't have any chance here in data set A that they are the same, so because there's no overlap, so that's why we can probably conclude that data set A gives us more evidence that there's a difference between those population means. All right, good job. All right, so our second review. So 90 people with high cholesterol are randomly divided into 3 groups of 30, and a different treatment program for decreasing cholesterol is assigned to each group. The response variable is that change in cholesterol level after 2 months of treatment, and an analysis of variance will be used, so an ANOVA test will be used to compare the 3 treatments. So what null hypothesis is tested by this ANOVA F test? So read over these answers and let me know what you think. Yay, raise the roof. So yeah, the answer is D here. Great job. So we're kind of just going through, the different steps of doing an ANOVA test. So our null hypothesis, remember, is also always saying that there's no change. So in this case, if there's no change, that means that the population means are all going to be equal. So remember that we have something that looks like this. So our mean 1 is equal to our mean 2, which is equal to, mean 3. So that means population means are all equal for the 3 treatments. So our answer would be D here. Remember, and we are talking about population means, so we can knock out A and C because they're talking about sample means. So that's no bueno. And then for B, it's talking about them being the population variances or being equal, which is not what we're talking about. We're talking about the population means here. So that's why it'd be D. So good job. It's kind of a tricky one. So you guys did great with that one. All right, so for a third one, we have that given the mini-tab expressed output above at the 0.05 alpha level, which pairs of summer sports are significantly different, just based upon this output. So look over these and let me know what you think. Yay, great job. So our answer here absolutely would be C. So if we look at this, we have, if we're looking at like the different groupings from our Tukey method here, Post-Hoc test, because remember our Post-Hoc test is basically asking, which specifically, which groups are different, you know, after we figure out that they are different. So in this case, you know, we see that swimming and running, they share a letter, and then volleyball and running also share a letter, you know, they share letter B. But then our swimming and volleyball, they don't share a letter here, you know, swimming is only A, volleyball is only B. So that's why we can say that probably that they're significantly different, because they don't share any type of grouping letter there. So our answer would be C. So good job. All right. Sad. The end. So I think everyone gave me your email, so thank you so much for that. Our next group review is going to be on Tuesday for our midterm review. Already the next midterm. Wow. So if you haven't already given me your Penn State ID, please go ahead and type that into the chat box, which I think you guys have. I'm so used to saying that, so never mind. If you have any other questions for this, let me know. If not, you guys are good to go for tonight, and have a great week.